Assalamualaikum warahmatullahi wabarakatuh, and hello, my name is MUHAMARRAZIF KAMRUSSAMAN, number matrix E2483310 from SCG1, and I'm from Group H. So, in this occasion, our group will be presenting about geochemical processes in soils, rocks, and waters. Before that, this is the list of our group members and the contents of our presentations. It includes introduction, 3 separate specific geochemical processes, which is soils, rocks, and water, applications and case studies, conclusion, and finally the references that we use. So, what is geochemistry? Before we deep dive into the geochemical processes, we need to know what is geochemistry. Geochemistry is basically a branch of geology and chemistry, respectively, at the same time, that study the Earth's chemical composition and how the chemical process dictate the distribution and movement of the elements in soil, rocks, and water. It links geology, biology, chemistry, and also environmental science together to create a, let's say, a very important field of study. So, why are we studying geochemistry? So, firstly, we study it to understand how the Earth, the cycle through Earth system works. You know, how it relates to lithosphere, biosphere, and the geosphere. Secondly, we study to trace the origin and transformation of natural resources. And finally, to assess environmental issues such as contamination, acid drainage, and groundwater pollution. So next, we finally arrive to the geochemical processes. First, I will tell you the definition of geochemical processes. Geochemical processes are the chemicals, physical and biological transformation that affect the concentration, mobility, and the form of element and compounds within the Earth, specifically in the soils, rocks, and water. This include processes such as weathering, mineral formation, dissolution, and redox reaction, and many more. Also biological interaction. What we will be examining in this presentation specifically, we will be examining the geochemical processes in soils, such as nutrient cycling, ion exchange. We also will be examining processes in rocks, geochemical processes in rocks, such as crystallization, alteration, and mineralization. And also finally in water, such as dissolution, redox, and how groundwater interacts. Understanding this process is very important, especially for sustainable resource management, to monitor the environment, and of course to solve problems that involve geoscience. Before we go more specifically to those 3 that I mentioned earlier, we need to know the connection between these processes. So, as you can see from the slides, we can see how this statistical diagram connects each of the sphere into each other through geochemical processes. For example, we can see how the biosphere and atmosphere connected through evapotranspiration, and how organic matter became sediments, or how sediments can contribute nutrients to the biosphere, to the living things. We can also see how the atmosphere can contribute to the formation of rocks from all the gases in the atmosphere, and how the hydrosphere connected through the atmosphere through evaporation and precipitation. That is for the introduction. We will go deeper into these geochemical processes one by one, and all those processes will be presented by my friends. Thank you. For now, I will be back for the case study and application later.
Hi, my name is NURUL, NATASYA, NAJWA, BINTI, Muhammad Zahari. and my metric number is E24A3265. I would like to explain about the geochemical process in soil. Geochemical process in soil refer to the chemical reaction and transformation that occur among soil minerals, water, gases, and organic matter. This process play a crucial role in controlling soil formation, fertility, nutrient cycling, and the movement contaminants in the environment. In total, there are 8 major geochemical processes that commonly take place in soil system. These include weathering, ion exchange, adsorption and desorption, precipitation and dissolution, redox reactions, organic matter decomposition, acid-base reaction, and completion. To begin with, let's look at the first and most fundamental process, which is weathering. Weathering is the physical and chemical breakdown of rocks and minerals into smaller soil particles. In physical weatherings, rocks are broken apart through mechanical force, such as in change in temperature, freezing, melting, rubbing against other rocks, and root pressure. While in chemical weathering, its reaction with water, acids, and gases like oxygen alter the mineral structure. Common chemical reactions involved include hydrolysis, oxidation, and carbonation. This transformation produces secondary minerals like clay and release essential ions such as calcium, potassium, magnesium, ion, and silicate into the soil. These ions become available for further geochemical process that sustain soil fertility. Following the weathering, the ions released into the soil solution engage in another key process known as ion exchange. Ion exchange is the process in which charged particles are swapped between soil surface and soil solution. Like soil particles, especially clay and organic matter, they carry a negative charge that attract and hold positive charged ions such as calcium, magnesium, potassium, and sodium. When plant roots absorb some of these nutrients, other ions from the soil solution replace them to maintain electrochemical balance. This process is essential for nutrient retention and supply and ensuring that plants can access the mineral they need to grow. As ions are held or released from soil surface, they also interact through process 3 is known as adsorption and desorption. Adsorption is the attachment of ions or molecules onto soil surface, while desorption is their release into the soil solution. This reversible process regulates how long nutrients and contaminants remain available in the soil. For instance, phosphate often absorbs tightly into iron or aluminium oxides, limiting its movement but also its immediate availability to plants. On the other hand, desorption can release these nutrients back into the solution under certain conditions. Together, this process controls nutrient availability, pollutant mobility, and soil buffering capacity. Once ions are in solution, they may undergo change in form through precipitation and dissolution. Precipitation is the formation of solid minerals from dissolved ions, whereas dissolution is the process where solid minerals dissolve into the soil solution. These processes are influenced by environmental conditions such as pH, temperature, and ion concentration. For example, in dry and alkaline soils, calcium and carbonate ions they may precipitate as calcium carbonate. In contrast, minerals like gypsum can dissolve in moist, acidic condition, releasing calcium and sulfate into the soil. This reaction affect the solubility and availability of nutrients and play a key role in soil structure and water retention. The next important process is redox reactions. Redox reactions involve the gain or loss of electrons by element changing their oxidation states. These reactions are essential in controlling the chemical form and mobility of elements like iron, manganese, nitrogen, and sulfur. In well-oxygenated soil, iron typically exists as ferriion, but in anaerobic or waterlogged condition, it gains as electron and becomes ferrous ion, which is more soluble. Similarly with manganese, which manganese 4 ion is reduced to manganese 2 ion. These reduced forms are more mobile and can be taken out by plants or lost through leaching. Other examples is nitric ion reduced to nitrogen gas during denitrification. Then sulfur ion reduced by hydrogen sulfide by anaerobic microbes. Redox reaction also affect soil color, odor, and microbial activity. They play a key role in nutrient cycling and can be influenced in the presence or toxicity of heavy metals. These reactions are influenced by the breakdown of organic matter, which is the focus of the next process. Organic matter decomposition is the breakdown of the dead plant and animal material by microorganisms and soil fauna. This biological process is carried out by bacteria, fungi, and earthworms, which break down complex organic compounds such as cellulose, lignin, proteins, and fats into simple substances. As decomposition occurs, essential nutrients like nitrogen, phosphorus, and sulfur are released in the form that plant can absorb. Some of the carbon is converted into carbon dioxide in aerobic conditions or into methane in anaerobic conditions. This remaining material, called humus, is stable and improves soil structure, increase water holding capacity, and enhance nutrient retention. Decomposition also produces next organic acids and influence soil pH, which brings us to the next process. The next major process is acid-base reaction. Acid and base reaction are chemical processes that influence soil pH and affect nutrient availability. Soil becomes acidic due to natural factors like rainfall and organic acid production, or from human inputs like fertilizer and acid rain. Basic substances such as lime are added to raise pH and neutralize the acidity. These reactions include the first one is hydrogen ion reacts with hydroxide ion to form water by neutralization. The second one, the calcium carbonate reacts with hydrogen ions to release calcium ions during lime reaction to reduce soil acidity. The next one, aluminium hydroxide dissolves in acidic conditions and release toxic aluminium ions. These changes affect nutrient solubility, with some nutrients becoming more or less available depending on pH. Soil pH also impacts microbial communities and processes such as nitrogen fixation. Lastly is completion. Completion is the formation of stable bonds between metal ions and organic or inorganic ligands in the soils. In this process, metal ions such as iron, copper, zinc, and manganese bind with organic molecules like humic acids, fulvic acids, or microbial products. This complex can protect metals from precipitation or immobilizations and influence their transport through the soil. For example, iron can bind to an organic acid and stay soluble even in conditions where it will normally precipitate. Compensation reduces the toxicity of some metals while enhancing the mobility and bioavailability of others. It plays an important role in micronutrient management and the behavior of pollutants in the contaminated soils. So that's all from me.
Hi everyone, my name is Muhammad bin Saharuddin. My metric number is E24A3271, and today I'll be talking about geochemical processes in rocks. So these are the chemical and physical changes that happen between rocks and their surrounding environment. So some of the main processes includes weathering. erosion, sedimentation, metamorphism, and the overall rock cycle. So each of these play a different role in breaking down, forming, or transforming rocks over time. These geochemical processes are essential for shaping the Earth's surface. They also control how elements are distributed and recycled in rocks. So without them, the landscape around us and even the resources we rely on wouldn't exist in the same way. So in short, geochemical processes are a key part of Earth's dynamic system. They help us understand how rocks change and how the planet evolves over time. So in this part, I'll be talking about geochemical processes that happen during the formation of igneous rocks. So igneous rocks form when magma cools and solidifies. So this process, both melting and crystallization take place, leading to changes in the composition of the rock. So there are four main geochemical processes involved, which are first one, partial melting, where only some minerals in the rock melt. Fractional crystallization, where different minerals crystallize at different temperatures because of the different temperatures where minerals crystallize. Third one, magma mixing, which combines magmas of different compositions. And assimilation, where magma melts and absorbs part of the surrounding rocks. These processes will then lead to igneous rocks with a variety of composition, like basalt, which is mafic, and granite, which is more felsic. This variation is why igneous rocks are so diverse. These rocks don't just form underground, they also make up a big part of Earth's crust. So, understanding these processes helps us understand how the planet's surface was built. So, in summary, igneous rocks processes are key to the Earth's geochemical system. They help us explain both structure of the crust and diversity of rocks we see around us. You can refer to the image above where a rock becomes more glassy when it is cooled faster, and it is classified as felsic when the silica content increases. So metamorphic processes occur when rocks are subjected to intense heat and pressure, usually deep within the Earth's crust. So these extreme conditions do not melt the rock, but instead cause the mineral to recrystallize and undergo chemical changes. This transformation changes the texture, structure, and mineral composition of the rock. Some key processes involve element migration, where atoms move within the rock, and fluid rock interaction, where hot fluids can introduce or remove certain elements. And the difference between isochemical metamorphism, where the overall chemical composition stays the same, and metasomic metamorphism, where new elements are added or lost. These processes lead to the formation of new metamorphic rocks such as schist, gneiss, and marble, each with distinct textures and mineral arrangements. Metamorphic processes play a major role in shaping existing rocks and crustal materials. As you can see in the visual above, shale, slate, phyllite, schist, and gneiss are arranged into an increasing metamorphism order, which means that shale experiences the least intense heat and pressure, and gneiss experiences the most intense heat and pressure. Surface processes occur on or near Earth's surface and play a crucial role in shaping the landscape we see around us. So these processes involve weathering, erosion, and mineral precipitation, all of which act on rocks and minerals exposed to the surface. So key processes include chemical weathering, where minerals break down due to reactions with water and gases in the atmosphere, leaching, which removes soluble elements from rock or soil, and precipitation, where dissolved minerals come out from solution and from solid deposits. So over time, these surface processes lead to the formation of soils, sedimentary rocks, and, and even economically valuable ore deposits. So altogether, surface processes are essential for a surface evolution and the cycling of materials in the environment. So the image above illustrates different types of chemical weathering, which are reaction with water, which examples hydrolysis, reaction with oxygen, examples oxidization, reaction with acid, examples acid rain or carbonization, and reactions with organisms, examples biological weathering. And finally, the sedimentary processes begin with the weathering of pre-existing rocks, which can either be mechanical or chemical. This breaks down rocks into clastic particles like sand, silt, and clay, as well as dissolved ions that can be carried away. These materials are then transported by agents such as water, wind, or ice, and eventually deposited in layers. Clastic sediments settle up as particles, while chemical sediments like limestone or evaporites precipitate from solution. There are also biochemical sediments which form through organic activity. Examples include coral reefs and coal. Once deposited, these sediments undergo compaction and cementation, where minerals like calcite or silica binds the grains together. Another process called autogenesis involves the formation of new materials, minerals with the sediment itself, such as pyrite. So geochemically, sedimentary processes are very sensitive to redox conditions. That means the presence or absence of oxygen can affect the minerals that form. So during transport and precipitation, element sorting and concentration also take place. So common examples of sedimentary rocks include sandstone, which is clastic, limestone, which is biochemical, and shale, which is fine grained and often formed from compacted mud. That is all from me. Thank you.
Assalamualaikum and good day everyone. My name is AINAA DAMIA binti GHAZI. My magic number is E2483223. Today I will discuss a fascinating and important issue in earth science and environmental chemistry, which is water geochemical processes. These are the natural chemical processes that take place when water interacts with minerals, soil, rocks, and the atmosphere. These processes affect the composition of water, regulate the transport of nutrients and pollution, and also transform landscape through the time. We will look at 7 different major processes that happen in water, which is weathering, dissolution and precipitation, ion exchange, redox reaction, hydrolysis, absorption and desorption, and lastly evaporation and concentration. Also, we will look at what each one is, how it works, why it's important, and present a clear example for each of the processes. The first process is weathering. It's the process that breaks down rocks and minerals at or near the Earth's surfaces. It can be classified into 2 main types of weathering, which is physical and also chemical weathering. Physical weathering involves the breakdown of rocks into smaller pieces without changing their chemical composition, often caused by the temperature changes, ice formation, and root growth. Chemical weathering, on the other hand, is change the chemical structure of minerals through reaction with water and gases such as carbon dioxide. This type is particularly important in geochemistry as it releases essential ions like calcium, sodium, potassium, and bicarbonate into natural waters. For example, when feldspar, a common mineral in granite, reacts with acidic rainwater, it breaks down into clay minerals and releases dissolved iron. The importance of weathering lies in its role as the starting point for geochemical cycle. It releases nutrients into the soil and groundwater, creates sediment, and increases surface area for further reaction, making it fundamental to soil formation, landscape evolution, and water chemistry. Let's move to the next processes, which is dissolution and precipitation. There are 2 opposing but closely related processes to each other. Dissolution occurs when water dissolves minerals, especially those that are soluble in slightly acidic condition. A well-known example in the dissolution of silicate is CaCO3 in limestone by carbonic acid in rainwater, which leads to the release of calcium and bicarbonate ion into the groundwater. This process is common in karst environments and is responsible for the formation of cave and sinkhole. Precipitation, on the other hand, happens when the water becomes oversaturated with ions, leading to the formation of solid minerals from solution. This can happen as water evaporates or when waters with different chemistries mix with each other. For example, that we can see in saline lakes or hot springs, minerals like gypsum or halite may precipitate out. The importance of these processes lies in their ability to control water composition, rock formation, and mineral deposition. They also influence water hardness, pH, and alkalinity, factors that are vital for both drinking water quality and ecosystem health. Next up is ion exchange. It refers to the swapping of ions between water and solid surfaces, especially on clay minerals and organic matters. Clay particles are negatively charged and extra positively charged ions such as calcium, magnesium, sodium, and lastly potassium. As water flows through clay-rich sediments or soil, these ions can be exchanged based on their relative concentration and affinities. For example, in coastal aquifers, sodium from seawater may replace calcium on clay surfaces, leading to a shift in water hardness and increased salinity. This process has a major implication for agricultural water use in soil chemistry and water softening technologies. It also plays a role in the natural buffering of pH and help regulate nutrient availability in soils. Ion exchange is especially important in groundwater remediation and contamination transport studies, where it influences on how pollutants like heavy metals move through the subsurfaces. Next process is the one of the important one, which is oxidation reduction or redox reaction. This process involves the transfer of electrons, leading to changes in the oxidation state of elements. These reactions are strongly influenced by the presence or absence of oxygen and are often driven by microbial activity. In oxygen-rich environments, metals like iron oxidize from soluble to insoluble, precipitating as iron oxides such as hematite. This is not only changes the color of rocks and soil, often producing red and yellow hues, but also immobilize elements that would be otherwise be mobile. In contrast, under reducing conditions such as a deep groundwater or wetland sediments, these oxides dissolve, releasing toxic elements like uranium into solution. Redox reactions are critical for controlling the mobility, toxicity, and solubility of many metals and metalloids, which directly affect groundwater safety and environmental risk. They also govern the behavior of the nutrients like nitrogen and sulfur in aquatic ecosystems. The next process is hydrolysis. Hydrolysis is a type of chemical weathering where water and weak acids react with silicate minerals, breaking them down into a clay minerals and release dissolved ions. It is one of the most slow but powerful geochemical processes that happen in the water, driving the long-term transformation of rock into the soils. A classic example that we can see that happen in the world, which is the reaction of feldspar with carbonic acid forming colonite clay and release the sodium, silica, and bicarbonate ion into the solution. Hydrolysis play a critical role in the soil development, nutrient release, and buffering the pH of the water. It also contributes to the long-term storage of carbon by helping to form the stable minerals that lock away, which is CO2. Next up is adsorption and desorption. Adsorption is the process by which dissolved substances like metals, nutrients, or contaminants to the surfaces of solid particles such as clay, iron oxide, or organic matters. Desorption is the reverse process where these substances are released back into the water when conditions such as pH or redox potential change. One well-known case is arsenic contamination in South and Southeast Asia, where arsenic absorbed to iron dioxide in oxygen-rich environments is released under reducing conditions. Absorption is critical for temporarily immobilizing pollutants and controlling nutrient levels in both surface and groundwater. Desorption, however, can lead to a sudden contamination when environmental conditions shift. These processes are vital for understanding pollution dynamics, for designing natural filtration systems, and for predicting chemical changes in aquifer, river, and also lakes. The last process is evaporation and concentration. Evaporation and concentration are key processes in the geochemistry of water, especially in arid and semi-arid regions. When water from lakes, rivers, or shallow basins evaporates due to high temperatures and low humidity, it leaves behind dissolved minerals. This causes the concentration of ions in the remaining water to increase. Over time, if evaporation continues and no fresh water enters the system, the solution can become supersaturated. As a result, minerals begin to precipitate and form sediment layers. This is how we get evaporate minerals like halite, gypsum, and calcite. This process plays a crucial role in natural water chemistry and the formation of mineral deposits. For instance, in places like the Dead Sea or salt floods such as Salar de Uyuni in Bolivia, intense evaporation leads to high salt concentration and the formation of economically valuable resources like lithium. Understanding evaporation and concentration helps geochemists predict minerals formation, manage water quality in reservoirs, and monitor environmental changes in closed basin lakes. In conclusion, these 7 water geochemical processes such as weathering, dissolution and precipitation, hydrolysis, redox reaction, ion exchange, absorption and desorption, and lastly evaporation and concentration work together to control the chemistry of Earth's water system. They are essential for understanding on how elements move through the environment, how landscape evolve, and how we manage resources like groundwater and soil. Whether we are studying pollution, farming sustainability, designing water treatment system, or exploring on how Earth has changed over time, these processes form the foundation of water-related geochemistry. That's all from me. Thank you for your attention. I hope you all understand it.
Alright, back to me again. Now that we know how the geochemical processes work, let's see some of the applications. The soil process can be used to improve the fertility of the soils. How does it work? It works through ion exchange, as we can see through the diagrams above. Ion exchange helps soil hold onto nutrients like potassiums and calciums, which they need to grow. By understanding this process, farmers can choose the right kind of fertilizer to fertilize their plants and get a better yield in conclusion. So next one, let's see the application of the rock process. We can use it to find metal ore through hydrothermal alteration. So how does it work? Hot fluids moving through the rocks can change the rock and leave behind valuable metals. For example, copper or gold, some of the common metal that we mine. So geologists can use this change to find a place to mine these useful metals. And the third application that we can look in this presentation is the groundwater quality. How can we check the groundwater quality? Through redox reaction. Different chemical layers in the ground affects what's in the water, like whether it has safe or harmful elements in it, such as maybe abundance of ions or arsenic. Knowing the redox zones helps scientists predict pollution and plan for clean drinking water or clean up. Now let's look at some of the case study. So the first case study, for a real world case study that we use in this presentation is arsenic mobilization in rice paddies, a redox reaction. This case study takes place in Mekong Delta of Vietnam, where a geochemical issue arises from interaction between soil chemistry and the practice of local agriculture. During this period, usually the plain is flooded for extended period of times, creating anaerobic, or what you can say oxygen poor condition in the soil, which cause a reducing condition that cause the microbial reduction of iron trioxide, which is normally act as a sink for arsenic by absorbing it to their surface. As the iron is reduced, a more soluble form, which is iron 2, bound the arsenic bound to this oxide is released into the soil solution. This arsenic can then be absorbed by rice plant, leading to food safety concerns due to the accumulation of the inorganic arsenic in the grains. So by understanding this redox-driven mobilization of arsenic, is essential for developing sustainable irrigation methods, selecting appropriate rice varieties, and minimizing health risks associated with arsenic exposure. Next, we can see another case study is about hydrothermal alteration at Mount Isa, Australia. Located in Queensland, Australia, is one of the world's most significant mining district, mostly for copper and lead. The origin of this mineral deposit in a complex geochemical processes known as hydrothermal alteration. Hot, metal-rich fluids move through the fractures and fault, altering the host rocks through both chemically and mineralogically. As the fluid interacted with the surrounding rocks, they triggered the precipitation of ore mineral like galena and sphalerite in specific zones. Distinct alteration patterns include serratic and carbonate zones. It helped geologists identify the pathway of fluid movement and locate economically viable ore bodies. This case study highlights the importance of understanding fluid-rock interaction in mineral exploration, and it also illustrates geochemical mapping that can on how geochemical mapping can direct mining operation toward high-value targets. And finally, the last case studies in our presentation today is a karst formation in Florida, the true dissolution. In Florida, the landscape is heavily influenced by karst topography, which forms through dissolution of carbonate rocks, primarily the limestone, of course. This geochemical process begins when rainwater absorbs carbon dioxide from the atmosphere and soil, forming a acidic rain with carbonic acid solution. As this is the slightly acidic water in seep into the ground, it reacts with the calcium carbonate in the bedrock, gradually dissolve and create underground voids, such as cave or sinkholes. Over time, this leads to a highly porous aquifer system that is essentially for groundwater storage. However, the system is also vulnerable to sinkhole formation, especially when groundwater level drops due to overuse or drought. This can be dangerous. The Florida case demonstrates how geochemical dissolution processes can shape landscape, affect water resource, and pose challenge for urban development, such as the sinkhole and infrastructure stability. I think that's all for me. We will end our presentation with a conclusion that will be presented by one of our members. That's all. Thank you.
In conclusion, geochemical processes are fundamental to the health of Earth's ecosystem and the survival of life. In particular, they regulate key elements such as carbon, nitrogen, and phosphorus that are necessary to sustain life on Earth. In the soil, this process not only enrich the ground with essential nutrients, but also help form minerals that improve soil structure and water retention. Similarly with rocks, this process contributes to the formation of minerals that help maintain the geochemical stability of the Earth's crust. While in water, geochemical processes play a critical role in maintaining water quality, which they regulate the chemical composition of water, ensure that it is purified, balanced, and suitable for ecosystem and human consumption. In this way, this process maintains the delicate balance of ecosystem by supporting nutrient cycling and ensures soil fertility, which is crucial for agriculture productivity and environmental health. Therefore, it is clear that these interconnected geochemical processes work together to sustain life on Earth, regulate the balanced ecosystem, and ensure the availability of clean water, which is vital not only for ecosystem but also for human survival. So that's all from us. Thank you.
And the thing is, this is the reference that we use.